I'm Rajesh Uppal, Director IDST. We bring sharp insights and foresight on defense, security, and emerging tech. Let's dive in.
We're entering a new orbital era, one where thousands of satellites, small but powerful, work together in coordinated networks circling Earth. These satellite constellations are transforming how we connect, observe, and even defend our planet. What began as a tool for scientists and militaries has now become the backbone of global infrastructure, driven by cheaper launches, miniaturization, artificial intelligence, and the insatiable demand for real-time data and connectivity. By 2030, over 20,000 small satellites, or smallsats, are expected to orbit Earth, reshaping how we communicate, monitor the environment, and conduct space-based research. Early pioneers like Iridium and Globalstar laid the groundwork decades ago, but today's mega-constellations, from SpaceX's Starlink to Amazon's Project Kuiper, are taking it to an entirely new level, bringing high-speed, low-latency internet to every corner of the globe. Unlike the massive, expensive satellites of the past, today's small sats are compact, affordable, and fast to deploy. Constellations in low Earth orbit, or LEO, provide low-latency communication and rapid Earth imaging. Medium Earth orbit, or MEO, powers global navigation systems like GPS and Galileo, while high geostationary orbit, GEO, offers persistent coverage for weather and broadcasting. Together, these layers form an intelligent, interconnected web encircling the planet. This revolution isn't just about communication, it's about capability. Earth observation constellations now deliver high-resolution imagery every few hours, helping farmers optimize crops, governments monitor deforestation, and responders track wildfires in real time. Others focus on navigation, synchronizing aircraft, ships, and autonomous vehicles with centimeter-level precision. Still others specialize in environmental monitoring, tracking carbon emissions, sea level changes, and melting ice sheets, giving us the data to act on climate challenges before they escalate. And beyond communication and Earth observation, satellite constellations are redefining national security. Small satellites now track missile launches, detect radar signatures, and relay encrypted communications, giving militaries constant, redundant eyes in the sky. Programs like DARPA's Blackjack are experimenting with resilient mesh networks, where data automatically reroutes if a single satellite is disabled. Constellations are also enabling real-time battlefield intelligence, precision targeting, and coordinated drone or hypersonic operations across continents. They serve as early warning shields, watching global flashpoints from orbit and linking command centers with troops in milliseconds. It's a glimpse of warfare's future, distributed, adaptive, and unstoppable. But managing these vast orbital fleets isn't easy. Space is getting crowded. Over 8,000 active satellites and tens of thousands of debris fragments already share Earth's orbital lanes. The danger of collisions is real, and the nightmare scenario known as Kessler syndrome, or debris collisions trigger cascading chain reactions, could make parts of orbit unusable for decades. To counter this, engineers are developing autonomous traffic management systems, AI-based collision avoidance, and active debris removal technologies using robotic arms and deorbiting sails. Another critical challenge is communication. To operate efficiently, satellites must talk to one another, often through laser-based inter-satellite links that transmit data at light speed without relying on ground stations. These optical connections are creating true space internets, faster, more secure, and less dependent on terrestrial infrastructure. Meanwhile, on Earth, ground networks are evolving just as rapidly. Parabolic dishes are giving way to electronically steerable antennas, flat, modular, and capable of tracking hundreds of satellites without moving parts. These systems make satellite internet more affordable, scalable, and ready for mass deployment. Technological advances are reshaping every aspect of this architecture. Miniaturized components now allow small sats weighing under 500 kilograms to perform tasks once reserved for bus-sized craft. Artificial intelligence enables onboard decision-making, letting satellites process and filter data before sending it home. Edge computing, quantum-resistant encryption, and modular design are becoming standard features. Propulsion and power systems are also evolving. New thrusters using iodine and other eco-friendly propellants allow satellites to maneuver more efficiently while meeting sustainability requirements for safety orbiting. Solar panel innovations and energy storage breakthroughs ensure reliable operations even in shadowed orbits. Cybersecurity has become another front line. As satellites carry sensitive data, they're increasingly targeted by cyber attacks, jamming, and spoofing. That's why modern constellations rely on encrypted links, secure onboard processors, and AI-driven anomaly detection to maintain mission integrity. And now the next great leap is already beginning: expansion beyond Earth's orbit into the vast arena of cislunar space. Future constellations will stretch between Earth and the Moon, supporting lunar navigation, communications, and resource exploration. Agencies and private companies are planning orbital networks that guide spacecraft, relay data from lunar bases, and connect the first human settlements beyond Earth. These early LunarNet and Moon-to-Earth constellations could become the backbone of a new space economy, enabling mining, science, defense, and human exploration in the Earth-Moon corridor. Looking even further ahead, emerging technologies promise to push these capabilities beyond imagination. Quantum communication networks could make space links virtually unhackable. AI-driven constellation orchestration may allow satellites to self-organize, repair, or even replicate components in orbit. And reconfigurable modular spacecraft could adapt their missions dynamically, from surveillance to deep space exploration, without ever returning to Earth. Ultimately, satellite constellations are much more than clusters of hardware in orbit. They're the framework of a connected, intelligent planet. They bring broadband to the unconnected, precision to navigation, foresight to environmental monitoring, and resilience to defense operations. Yet their success depends on something deeper than technology: global cooperation, responsible stewardship, and sustainable design. As humanity builds this new orbital infrastructure, we're not just wiring the sky, we're laying the foundation for the next chapter of civilization. A chapter where every signal, every sensor, and every satellite brings us closer to a truly connected world. And beyond, to a universe that's finally within our reach. Thanks for watching. Subscribe, follow, or visit idsth.com for more cutting-edge defense and tech insights. See you in the next one.